In the previous video, we were discussing the common neural network, or we normally call it as an artificial neural networks. So please, it's pretty common that in the previous discussion, the neural networks that we discussed before, most of the time in more popular way, we call it as an artificial neural network, or we abbreviate it as ANN. In this video, we are going to discuss another neural networks that is called as a PNN, probabilistic neural networks. Please note that this is completely different approach, but it also uses the idea of how neurons work in our brain. It is inspired by biological things, neurons in our brain, but the approach is different than in artificial neural networks in ANN. We call this as probabilistic neural networks, or PNN. So what PNN is? PNN is also a classifier. It maps any input patterns to number of classification. It's pretty simple, of course. All classifiers does that. And it can be forced into a more general function of approximator. So I will come back to this point later. So in this case, for PNN, the nice thing of PNN in other approaches that we have already discussed before, from the sample that we have, we assume that the density function, the distribution of the population in our data is normal. It's normally distributed, or you can assume it with one specific distribution. Actually, it's not only constrained to normal distribution, but we assume the population of our data based on the sample that we have to have a certain probability function, where the most common one, we assume it as normally distributed. And PNN here, the structure of PNN is very firm, it's fixed. It's not like ANN, artificial neural network, where we can add the number of layers, we can add more neurons, but the structure of PNN is fixed. It always has 4 layers: input layer, pattern layer, summation layer, and the output layer. So this is the simple illustration on how the network normally look like for PNN. So we always have 4 layers. We have the input layer for the first layer, and in here for this illustration I have 7 neurons in the second layer, which we call this layer also as a pattern layer. We have 3 neurons in the third layer, or summation layer, and we have an output, the output of classification, which we call it as an output layer, of course, here. So what is the nice thing of PNN, the probabilistic neural network? When we were discussing naive Bayes last time, or even when we were discussing ANN, artificial neural networks, in the previous video, if we have a sample, then in our examples, we always consider the population of the samples are normally distributed. You still remember our discussion in naive Bayes last time? We have a collection of data from a group of children and a group of adults. We collect the weight and the height of the individuals, of the children and the adults. So if you still remember this story, there are few samples of children with all of the weights and the heights. There are few data of weights and heights of adults, right? And what we did last time, based on these samples, we assume that the weight of the children are distributed normally, as well as the height of the children, the weight of adults, and the height of adults. Based on these samples, we assume that the population has a normally distributed density function, right? That's what we did in naive Bayes last time. Actually, you don't have to take normally distribution. You can use any kind of distribution. You can use uniform distribution if you want. But what I want to mention, you need to take an assumption of the probability density function when you want to do naive Bayes last time, right? In this probabilistic neural networks, we are not taking an assumption on how the distribution in the population, but instead we estimate what the probability density function in the population will be based on the samples that we have. So this is the technique, Paulson window. Paulson window is a technique to estimate a probability density function of a population from the sample that we have. But the estimation is non-parametric. If you consider a normally distributed probability density function, that is definitely parametric. Why? Because if you still remember the equation, the PDF, the probability density function of normally distributed population, there is a function where this function, the PDF, the probability density function, is represented by two parameters only, right? The mean and the standard deviation. So as long as you have these two numbers, you assume that the population is distributed following the PDF function of normal distribution that only represented by two parameters, mean and standard deviation, right? That's how a normal distribution function works. But Paulson window is a non-parametric approach, which means you are not representing it as a function as per se that has a parameter on it, but you estimate the shape, and the shape can be anything. Okay, so it's not represented by two or three parameters like in normal distributed function, but Paulson window can approximate any shape of distribution function. So how does it work? The concept actually is pretty simple. Let's say you have a population and you collect samples out of this population. For illustration here, I have, if I'm not mistaken, I have 32 samples here represented by these blue dots. So I have 32 samples taken from a population. And then the probability density function from this population looks like this. From the population. So this is the probability density of the population. But this probability density function of this population, we never know, right? We cannot collect all of the individual from the population to calculate the probability density function. We cannot do that. We cannot collect all of the data. All we can do is only taking few samples from the population. And then we estimate the probability density function. So the real probability density function of the population, we never know it. We will never know it. That's why I put it in gray now. We never know this, but this is for illustration only. all we know, all we can get is to estimate it from the samples that we take from the population. So how to estimate the real probability density function, the ground truth of this probability density function out of these 32 samples? That is the question. So what I'm going to do from all of these samples, I will split it into few groups. I split it into, I don't know how many groups here, 10 groups. And then for each groups, separated with different regions like this, I calculate number of samples for each group. So the first group here, I have no samples, right? No samples. That means the probability of having a sample in this group is 0. From the second group here, I have 2 samples out of these 32 samples. That means the probability to have individual within this group will be 2 over 32. Okay. For group number 3, I have 4 samples within this region. So the probability of having an individual from this group will be 4 over 32. And then I do it again for the rest of the groups. I have 5 samples in here, so the probability is 5 over 32, and so on and so forth. So it's like developing a histogram here. It's pretty simple, you know how to do histogram there. But in our spatial histogram here, this region, because what we are going to draw is here is the probability function. So the nice thing, the unique thing of the of our histogram here, the area, let's say the area of this rectangle here corresponds to the probability. So this area, let's say this area is 2 over 32. This area is 4 over 32. So this area is double than this one. This area corresponds to 5 over 32, 3 over 32, 2 over 32. So if you look, this area is equal to this area, and so on and so forth. So the area of my individual block here, of my histogram here, should represent the probability of that corresponding area, the area of this box. Okay, so then this looks like a probability density function, right? If the width of this, if I know the width of this region, let's say the width is equal to n here, and this area is equal to 2 over 32, then obviously this height will be equal to 2 over 32 divided by n, right? Right? The area of this rectangle is 2 over 32. The width is n, so the height is area over the width. Same thing to the second one. This height should be 4 over 32 divided by n. Right? What does it mean? What does it mean again? Then this height, all of this height, represent my estimated probability density function. So this is my estimation of this gray line there. Obviously, if you have more samples from the population and then you split it into more regions, you will have a finer step-like function there, and then I expect it will resemble more to the real probability density function, the probability density function of the population, right? That's pretty intuitive, isn't it? You have more samples, discretize it even finer, and then you can approximate the probability density function of the population. Okay. I have another thing here, another interesting thing. So this is what I did. I approximate, I represent the probability of each region here with a rectangle, with a rectangular form like this. Right? But then something comes in my mind. Why do I have to approximate it as a rectangle here? I have a scientific freedom to approximate it with any function. This is just my assumption to approximate it with a rectangle. Why don't I approximate it as second order polynomial like this? You can choose any function to approximate the probability of each region there. And now I will try to approximate it with a quadratic function like that. If I do it like that, then I have to do it consistently for the other groups, right? That means the line that covers this area, I indicate it as red line here, should be my estimated probability density function. But if I compare this red function with the gray one, the real probability density function, the real PDF, I rather abbreviate it as PDF here to make it shorter. The red PDF it doesn't look very nice compared to the gray one. It doesn't resemble very well. So my approach to represent the individual PDF, the individual probability density function with a quadratic function is not really good in here. So I have another thought again here. Instead of using quadratic function or rectangle, for one group, I will approximate it with a normally distributed PDF. Whereas what we have already discussed before, one PDF here is a parametric function that is represented by two variables. The mu is the middle value of this PDF, of this normally distributed PDF, and sigma, where sigma represent how wide this function will be. The smaller the sigma, the more spiky my plot will be. The larger the sigma, the wider my PDF will be, right? Now I will approximate it with a normally distributed PDF where for each of the groups, mu is the middle value here. And for sigma, I will just take any number. So I will just use a certain sigma for this approach here. I just take it from the air. So I just take any arbitrary sigma then here. I do it for this group, and then I have to do it for the rest of the groups, right? And then after that, what do? I have to sum them all to come up with the estimation of the probability density function of the population, right? So I sum them all, and then after I sum them all, if you take a note here, there are some overlapping areas there, then I have to double it if I have overlapping areas there. So after I sum them all, it becomes something like this. So this is my estimated probability density function. While the ground truth of the probability density function, the probability density function, the PDF of the population looks like the gray one. So if I compare this, well, this red one resembles more to the gray one compared to when I use rectangle, or even worse when I use quadratic function, right? So this looks like a best approach to me. The question now, how should I select the sigma? It will be something like this. If I choose small sigma, and then if I do it for the rest of the groups, and then I sum them all, this will be my estimated PDF, which looks more like the one that we did with the quadratic function. It doesn't look good. On the contrary, if I choose large sigma, what will happen? I sum them all. If you sum them all, then it will look something like this. So you can imagine the larger the sigma, the total PDF, the estimated PDF for the population will resemble again to normally distributed function. So if you choose sigma to large, then it's just nothing else as if you estimate the distribution of your population as normally distributed based on all of the samples that you get. So the question now, how to pick the right sigma? The answer is, I don't have an answer for that. You have to do some trial and errors, check it, what will be the best sigma, what is the most reasonable sigma to choose. If I look at the data here, how the data is distributed, I have two areas here with a denser sample here. So looking at this data from the samples, I expect I will have a distribution with two peaks. So based on that qualitative judgment, then you can properly choose the nice sigma to estimate the probability density function of the population. Now let's go back to the network itself, the probabilistic neural networks. As I have already mentioned, the structure of this network is pretty fixed. We always have four layers. The first layer is the input layer. So if you have two inputs, then you will have two neurons in the first layer. And the second layer, what we call is a pattern layer, is the most important layer here. The number of neurons in this layer is equal to the number of the samples that we use in the training. Okay, and each of the neuron here, because you have the training number there, the training data here. Remember again, each of the neuron here correspond to each data in your training set. So each of these, based on that training data set, we will construct one PDF, one normally distributed PDF, using that training data as the mean, and you choose sigma with whatever you want. Okay, again, right? If one neuron here corresponds to one training data set, then you can construct one normally distributed PDF there. You use that data as the mean in your normally distributed PDF, and you take sigma, whatever you want, because we need these two variables to construct PDF of population. Mean and sigma. Mean is taken from the data, sigma you choose whatever you want. But of course, there are some constraints there. If it is too small, then you will have this spiky problem that we discussed before. If it is too large, then you just approximate your entire population as a normally distributed function, which might not be correct. And the third layer here, layer number 3, you just simply sum the output of each neuron in the second layer for the corresponding classes. So the color here represent different classes. We have 3 classes to distinguish from our input there. Actually, one more that I need to note, this is not a summation, actually, it's averaging. So if you have 2 neurons as an input to this neuron, you you will not just sum it, but you will divide it by 2. You have to average it. For this one, after you sum it, you have to divide it by 3 because you have 3 neurons as an input to this neuron. Okay, let's talk a bit more in detail with some examples for illustration later. Let's take a look on this example. This is very simple example actually. So I have one input to classify. X is the input from my training data sets, and the second column here represent the class associated to the input X there. So these are my samples. I have 1, 2, 3, 4, 5, 7, 8. I have 8 samples there. The first 5 data set corresponds to class 1 because I have 2 class problem here. The remaining 3 corresponds to class 2. So if the input in my training set is 2, 2.5, 3, 1, 6, those belong to class 1. When the input is 6, 6.5, and 7, those belong to class 2 in our problem. And then the problem here, we need to determine what is the class if the input is 5. If I look at these training sets, well, just look qualitatively from these training sets, I can see that if X is small, 2, 2.5, 3, 1, they will belong to class 1. If the input is large, they will belong to class 2. Saying that small x is class 1, large x is class 2. It's very simple classification actually there. There is one value of 6 here that sometimes is classified as class 1, sometimes classified as class 2. So I'm not really sure. Perhaps this might be some uncertainty in our data set. This might happen in your data. But qualitatively, if I look at these training sets, what I can say, if X is small, the class is 1. If X is large, then it will belong to class 2. But where is the border? We still don't know that, right? So now again, back to the problem, we need to determine the class if X is equal to 5. We are going to solve it using PNN, probabilistic neural networks. So I will start to sketch the networks first. It will start from the layer 1 with one input, one neuron. And then layer 2, I have 5 neurons that corresponds to the first 5 inputs in my training sets that are correlated to class 1. And then I have 3 more neurons corresponds to class 2 in my training set. Each of these neurons will represent normal distribution function. So let's say the first neuron here will represent a normally distributed PDF, probability density function, with mu, the mean value, equal to 2 for the first one, and with a sigma, that something I can choose by myself. So I choose any sigma that I want, but the mu for the first neuron is 2, the mu for the second neuron is 2.5, for the third one is 3, 1, 6, and the remaining 3 that belong to second class will be, the mean will be 6, 6.5, and 7. So I will construct individual normally distributed PDF for each of these neurons, just like what we did when we discussed Parsons window. So each of these individual PDF is represented in each neuron here. but the middle value here is the value in my training set. Okay, so so if I go back, then each of these will has each individual PDF, again with the mean of these individually and sigma, whatever you want, you choose it by yourself. Again, there are some constraints, of course, there we have already discussed it before. If it is too small, if your sigma is too small, it will become too spiky. If it is too large, then your estimation of the PDF of your population will resemble to normal distribution. Okay, let's go back to this network. So I will have 5 plus 3 neurons in the second layer, and then I will evaluate the probability for each of these neuron for the input x. So I have to calculate the probability of x for this different probability density function. And then in the next layer, I will just sum them all. I have already mentioned it before, it's not summation, but I have to average them all for those neurons in the second layer that corresponds to the first class, and I have to do it also for those neurons in the second layer that corresponds to the second class. I have to average them all. So in that case, then in third layer, in layer 3, I will have 2 neurons where the number of neurons here corresponds to the number of classes that I want to classify. And then the last layer here, this will just compare which one is the largest. The largest value is the winner, which means whichever the largest, that will tell us what is the class of the new individual X there. Okay, so that is the concept. Let's try to calculate, let's try to evaluate this problem using PNN step by step for this example. Okay, so I just choose certain sigma. For simplicity, I will just choose sigma equal to 1. We will see later on whether sigma equal to 1 is too large or too small. We will check it later on, but now for time being, let's just choose sigma equal to 1. And then I construct the normal distribution PDFs for each of the training samples. I will start from class 1 here. So because I have 5 samples there, I will construct 5 individual normally distributed PDFs here. The first one here, the leftmost one here, corresponds to data number 4 with a mean equal to 1. So this is normally distributed PDF with mean of 1 and sigma of 1. The second one from the left here has a mean of 2 that corresponds to the first data set. The mean is 2. And the sigma is also 1. So I just apply the same sigma to everyone. The third one from the left, the middle one, corresponds to the second data set, where the middle value of the third PDFs here is equal to 2.5. The fourth one, the middle value is 3, corresponds to the data set number 3. And the last one, the middle one is 6, corresponds to the data set number 5 here. Looking at how this data is distributed, 2, 2.5, 3, 1, and I have one more data equal to 6, which is relatively far from this bunch, the first 4 data set. I expect the distribution of this population will have 2 peaks, just like what we have here after I sum all of these 5 PDFs. So in my first judgment, probably selecting sigma equal to 1 is a good choice in here, because I will have 2 peaks. Then I do it for the second class now. The first PDF here, the middle value, the mean will be 6. That corresponds to data number 6. The middle one is 6.5. The right one is 7. I sum them all, and then it will be something like this. So I have, at this point, then I have already constructed the second layer in our network. Let's go back to the network now. And then we calculate the output out of this second layer to come up with a neuron on the third layer. So what I'm going to do now, I will evaluate it for x equal to 5, the new individual that we want to test its class. So I will take again the same plot again here. And where is 5? 5 is here. I will calculate the average probability from all of these 5 probability density functions. Again, as we have already mentioned, we have 5 here. 1, 2, 3, 4, 5. That corresponds to all of the training sets that belong to class 1. And then the blue one here is the summation, all of these 5. So what we are going to find now is the total probability for x equal to 5, which is this one. What we want to find actually is not the total, but it's the average. So after I get the total here, I have to divide it by 5 because I have 5 samples that belongs to class 1 now. So I just have to calculate what is the value in here. And this is the calculation of the summation and the averaging. So I calculate the probability that corresponds to the first PDF. The first PDF will have a mean value of 2. So actually it's the second PDF here. I'll just calculate the probability of having x equal to 5 for probability density function with a mean of 2 and sigma of 1. So I will calculate it using this function. And the second term here corresponds to the other PDF here, 2.5. 2.5 is the third one. I calculate the probability in here. Mathematically, I can calculate it like this. The third one corresponds to the third PDF. The fourth one corresponds to the fourth PDF with mean of 1 here, and then the last one is this PDF, right? So I just sum them all, but what I need is the average. I divide it by 5, and then I will get the probability of having the value 5 out of this probability density function. So the summation is equal to 0.318, which is this one. I divide it by 5. This is the probability of the value of 5 as an output in my third layer in my networks. So how does this corresponds to our definition, our conclusion in finding the probability of the value of 5 to become the first class? This actually related to the one slide that we discussed it when we discussed Bayesian network last time. So what we want to calculate basically is the total probability the probability of X belongs to class 1 in our network problem there will be equal to the probability of X equal to 5, given that that it belongs to the first group times the probability of that groups among all, and then summing again to the other probability. So taking to this total probability calculation analogy, PAB, if we look at this basically what PAB1 in this slide. PAB2 basically is the second term. PAB3 basically is the third term, and so on and so forth. So basically then this value calculates the probability of 5 given that the population where it belongs is in this distribution. And for the second term, it's the same thing. It calculates the probability of 5 that given that it will belongs to the second small group here, and so on and so forth. And then we multiply it by the probability of this group individually, but we have 5 groups here. All of them share the same probability function, so they will have the same value here, and then I have to divide it by the total probability. So nothing more, it is just an averaging, because all of these have the same values, and total of PB1, PB2 until PBN. In our case there we have only 5, so PB1, PB2 until PB5 there. The sum of all of those will be equal to 1. The total probability of B1, B2, B3, B4, and B5 will be equal to 5, and all of them shares the same value. So basically then 1/5 is the individual PB1, PB2, PB3, PB4, and PB5 in our case here, which basically this area having normalize it by the total number of 5. Okay, so this basically what we are calculating here is the probability. Let's go back again to the network. So the probability of having this value 5 belongs to the class 1 is apparently 6.36%. Then we have to do it again, the same thing, but we have to check it for the second class. When X is equal to 5, then I can calculate the probability. I calculate it individually for first one, second one, and third one, sum it and divide it by 3 because I have 3 samples then. And then the result, the probability is 14.18%, which is bigger than the previous one. So from here, I will conclude that X equal to 5 is classified as the second class there. This example gives you a brief overview on how we do it for PNN, how we define classes for PNN. Let's take a look here. So previously we just choose sigma equal to 1. What will happen if I choose smaller sigma? So if I choose sigma equal to 0.2, I will have this shape for class 1 PDFs. For the estimated PDF of the population of class 2 will look like this. What will happen if I want to test it for X equal to 5? So X equal to 5 will be here. Yeah? If you look at this, both of them will give a zero probability. And then at the end, because of this spiky probability density function, you will end up with zero areas here. If both of them will give a zero value, then you cannot conclude anything about the classification of x equal to 5. On the other hand, if you choose sigma too large, then both of them, for class 1 and class 2, both of them will look like a normally distributed population. So in that case, there is no point to use PNN in here, because you don't really estimate the probability density function of each population properly in this case. Okay. So this, just to summarize again, what is the effect of sigma? As we have already discussed before, if sigma is too small, then we will come up with a spiky probability density function. You will get a difficulty in classifying the new individual, because you might end up into all zero probabilities and you cannot deduce anything from that. On the other hand, if sigma is too large, then you will just approximate the population PDF to be a normally distributed, to be Gaussian. And then the beauty of PNN, you will not get it anymore. Okay. So the previous example that we just discussed, I give an illustration of single input. Let's take a look now how it will work if we have multiple input. So this is an example of a two input classification problem. I have two inputs, x1 and x2, and then I have three classes to distinguish these inputs. I have 7 training sets here. The first two belongs to the first class. The next two are from second class. The remaining 3 from the class 3 there. Now the problem again here, I need to determine the class for this data, where x1 is 3.5, x2 is 3 in here. Let's take a look on the data first. The data set that belongs to class 1 has an input 0, 0, and 1, 1. If I look at how the data is distributed, I doubt if this new individual will belong to class 1. Right? Both of them have a small number, so I don't think it will be categorized as class 1. But if I look at class 2, it's 0, 3, 1, 4, while for class 3, I have 3 training sets, 3, 1, 4, 1, 4, 3. This I will get a difficulty here to classify this new individual, because the first input here is large enough to be classified as class 3, but the second input here is also large enough to be classified as class 2 there. So I doubt if this new individual will belong to class 1, but I cannot estimate roughly whether it belongs to class 2 or class 3. So let's try to analyze it using PNN, using probabilistic neural networks. I will start it with sketching the networks. So the network starts with the first layer consisting 2 neurons, and then for the second layer, that will correspond to the number of the training sets. I will have 2 neurons because I have 2 data in my training set that corresponds to class 1. I indicated with the blue neurons there. I have 2 more neurons that corresponds to class 2. I have 3 neurons that corresponds to class 3. It's just a nice color there, blue, red, and green. And then each of these neurons will represent the joint probability of x1 and x2 at these two mean value. So same like before, but now we have a joint probability because we have two variables. So the probability density function that we have to sketch should be in three-dimensional space because we have a joint probability density function now in here. So for this neuron again, then I will have joint probability density function with these two mean values 0 and 0. For the second neuron, same thing, joint probability density function with a mean 1 and 1. For the third one, I will have joint probability density function with a mean of 0 and 3, and so on and so forth, right? And then I need to evaluate the joint probability density functions, all of these joint probability density functions to these two inputs. And then after that, in the next layer, I have to average them all, right? Same like before. And then the last one is the competition, which one is the largest. That will tell us what is the class of this new individual x1, x2. Okay. Let's try to calculate it one by one. I will not calculate them all, but this just to give you an illustration on how I calculate it. Let's start it from the first neuron, the very first neuron. So how we calculate the joint PDF, the joint probability density function, the formula is same like before, but then you have to join these two probability density function because you have one probability density function from the first input and you have another PDF from the second input. So you have to join them by summing it in exponential form. Actually, what it does, you multiply these two probability density function. So you multiply the first one with second one again, but then if you multiply two exponential function, basically what you do, you just sum it in this exponential form. So actually what we are doing is this times exponential of the first PDF times the probability again for the second PDF. But you have exponential of something, let's say exponential of A times exponential of B, then what you have is equal to exponential of A plus B. So this will be the most compact form of a joint distribution function. So we have to calculate it for all of these neurons in the second layer. Let's say if we want to calculate for the first neuron here, then you will have to calculate it as follows. You have x1, which is 3.5, and you have mu1, 1, that is the mean from the first training set for the first variable. So it will be 0, so mu1, 1 here will be 0, x1 is 3.5, x2 is 3, and x1, 2 is the mean for the second PDF, the second input x2 for the first data set, which is also 0 in here, right? So x1 is 3.5, mu1, 1 is 0, x2 is 3, mu1, 2 is 0 also. You have to calculate this. Now you have to do it again for the second neuron. But then in here, x1 is still the same, 3.5, but the first mu here, mu21, is the mu from the second data set that corresponds to this neuron, of course. So mu21 there will be equal to 1. x2, this is supposed to be x2, is 3. I made a mistake here. Please take note, this should be x2. And mu22 is the second input from the second training set, which is 1. So you have to do that for all of these neurons in the second layer. And then after that, you take the average of these two output, right? I just sum these two divided by 2 because I only have 2 neurons in the second layer that corresponds to the first class. If I average it, apparently I calculate it, I average it, and then apparently the probability out of this neuron will be equal to 0.0005 or 0.05%, right? And then I do it again for this. So if you look at this, out of this neuron, I just take the average of the joint PDF from the first input. If you look at this, the first input, I mean the first input for the second class, 3.5 minus 0, 0 is coming from the first input in the third data set, plus 3, 3 is the second input, minus 3 is the second mean that is coming from the second input in my third data set here. And then I average it with the one from the fourth data set, 3.5 minus 1, right? And 3 minus 4. I sum these two divided by 2, I get 0.0023, 0.23%. So the previous one is 0.05%, this one is 0.03%, and then I calculate it again for the last neurons here in the third layer. So I again average it here, but I have 3 neurons in the previous second layer there, same like before. The first term here is coming from the dataset number 5, 3 and 1. The second term from the 6th dataset, 4 and 1. The last one is 4 and 3 coming from the last dataset. I sum them all. I divide it by 3 because I have 3 samples here that belong to class 3, and then I will get 5.95% probability. This seems to be the largest among these 3 output. So from here I can conclude that this is the winner. This new individual 3.5 and 3 belongs to the class 3. Okay. All of my analysis here that we just discussed were taken with sigma equal to 1, but this might not be the best sigma. You have to try it with different sigma to see if there is a consistency on it or not. So just for the completeness of our discussion, this is the joint probability functions for class 1, class 2, and class 3 when I take sigma equal to 1. Okay. I don't know, to me it looks nice. I still have different peaks here, but they seems to be from one population. So this is from class 1, class 2, and class 3. In class 3 you have 3 peaks here. Not necessarily you need to have 3 peaks because you have 3 individuals in the training set. You don't need to have 2 peaks because you have 2 data in these 2 different classes. But yeah, this is something that I cannot tell to you with sigma that you have to choose. But if you compare it, when you take a smaller sigma, so this is when I use sigma equal to 0.2 for class 1, class 2, and class 3 from the data set. I just see here as 2 or 3 separated population. So this definitely is not good because you might have some regions where the probability is always 0. As well as if you take too large sigma, then you only see one normal probability density function in each of the classes here, especially in our case here, in our example here, for class 1 and class 2, we only see one joint probability density function here. Okay, so that illustrates on how we use probabilistic neural network for classification problem. One thing that you might need to highlight here, the beauty of this PNN is that we do not assume the PDF of our population, but the PDF of the population is estimated from the underlying data.